On camera.
So that just got recorded. Can you go sit down, please? I have to write on the board.
Oh, so my face is not going to be recorded. That means I can say as many fucking expletives as I want. Fuck, shit, ass, face. Not.
What is the pencil writer?
The pencil writer is crazy, but.
What is the marker writer? Highlighter, writer. Okay, thank you. Okay, now go. Let me log in.
You stabbed me!
Is everything visible on the screen?
Yeah.
Okay. So, let's just quickly review what we were discussing before. So, you know the optical theory of solar cells now, right?
Ni-hao.
Now we're going to dive into some more material.
Ni-hao.
Including the orbital dynamics of solar cells. So, here we go.
Oh, it loaded.
Okay, so one of the assumptions we made in that, in the derivation of the relativistic reflection equation was that delta V equals 0.
Mm-hmm.
Right?
Yeah.
That means solar celling wouldn't work because then the photon wouldn't impart momentum to the light cell, right? Mm-hmm. So that's actually a faulty assumption. It's a good assumption for reflection, but for solar celling, not so much. So first of all, we discussed this, right? There's 4 different types of orbits, right?
Yep.
Now we're going to talk about the force exerted on a perfectly reflecting solar cell. So the force exerted on a perfectly reflecting solar cell. So a cell like this, so you have light coming in and light going out. So far so good?
Uh-huh.
Okay, so here's how that's gonna go. Give me 1 second.
Can I ask a question?
Yes.
What if we set a new parameter, delta, which would state how reflective it is?
Yeah, all of that's coming up. So.
Why do we have to make it fully reflective?
Because otherwise the physics doesn't work out. But if you want, that parameter is there, and I'll show that to you. So here is our solar cell. Here's our solar cell, right? Here is sunlight. First of all, what do we calculate all angles of incidence with respect to? The normal, right?
Mm-hmm.
So here's the normal to the cell. Here is light coming in. Oh, oops. By the way, this is not a relativistic solar cell. It's just like a traditional solar cell.
Wait, where did you get your final result, Tom?
Wait, yeah, you were sleeping by the time I wrote the final result, but there you go.
Here it is.
Yes, you need some trigonometric simplifications to get to the final result, so just write it down as soon as you get the frequency, as soon as you get to that last step. So here we go, look. So here is the incident light beam, let's call it U sub I for incident. And here is the reflected light beam, let's call it U sub R for reflected. And let's say the angle of incidence and reflection are alpha. This is of course non-relativistic, so we can assume that the angle of reflection is the same as the angle of incidence. What happens actually is for a light cell, when a photon hits it, so when a photon hits the light cell, right, that photon gives it some momentum, and then the photon that after it's reflected, that gives it another momentum kick. There's actually 2 momentum kicks. Kicks.
Oh, kicks.
So one from the incoming photon and one from the outgoing photon. Does that make sense?
Mm-hmm.
Okay. So, do you know what the definition of force is?
That's a lowercase f.
That's fine. Want to use a tissue?
No. Damn you.
Is everything still... You know you're going to watch this on the plane, right?
Mm-hmm. I'm going to regret... Yep, everything is visible on camera.
Okay. What is the definition of force?
MA?
Many ways to define it. MA, it's the derivative of the potential with respect to position. It's the derivative of momentum with respect to time. Another way you can define it is it's pressure times area, right?
That's crazy.
Because pressure is force per unit area, isn't it?
Mm-hmm.
I mean, that's literally how blood pressure is defined, in fact. So force is the radiation pressure times the area of the solar cell, right?
What's radiation pressure?
Oh, it's the pressure coming from the photons that are emitted from the sun. That's just a name.
Okay. Sure.
Okay, now, so far so good with this?
Yep.
Now, this is the force due to the incoming photons. Of course, force is a vector, right?
Mm-hmm.
Can you maybe look at the screen?
Oh, just give me a sec.
Okay, this is the force due to the incoming photons, right?
Mm-hmm.
But what direction do they impart a force?
Is it perhaps in the direction that they're hitting the mirror?
Well, this is actually gets a little subtle. Here's the full force law. It's the dot product of the incident vector with the normal vector times the incident vector. So let's try to break this down and understand what's going on. First of all, the dot product with u sub I and n. What does that mean? That's just cosine of alpha, isn't it?
Yeah.
So wait, hey, what does that mean? That means when the angle is 0, we have the maximum force.
Because it's hitting straight at the normal.
Aha. And if the radiation comes in, if a photon hits it like this, then it doesn't get much force, right? Because it's hitting in a very sideways motion, and so it doesn't impart that much momentum.
So we can kind of spin it around to change that angle and change how much force is being imparted.
Exactly.
You look like an eldritch demon. Thank God your face is not on camera.
So that's where the cosine alpha. Can you not? Wait, what are you doing?
Nothing.
Is everything still visible?
Yes.
Don't fool around with the camera. You need this in India.
Yes, I do.
So this is the force, incident force, right? Now let's write down the reflected force. What is that going to be? Well, this is going in that direction, right?
Yep.
So it's minus PA. Dot product of the reflected unit vector.
That's also alpha, right? Cosine
and
alpha.
that's also alpha, right? Because the angle of reflection and incidence we assume are the same. So far so good?
Yeah.
Sorry. Okay.
Wait a second. But isn't the unit vector UI equal to minus UR?
Yes.
So doesn't that mean FI and FR are the same?
Sorry. Should be UI then. Very good.
Okay, sure.
So actually, yes. So the more formal way to write it is U sub R, right? So they're the exact same. But of course, U sub R is minus U sub I. That's how you get this guy. Does that make sense so far?
Yes.
Am I making sense or no?
Yeah.
So what is the net force?
Well, it's
The
FI
incidence plus reflected, right?
but FR is just FI.
Exactly. So it will be 2 PA, isn't it?
No. 2 PA UI cosine alpha.
Does that make sense?
Yeah. Don't you add the UI cosine alpha?
Let's see how I got that, shall we?
What?
Let's see how I got that, because it's not trivial. So it's PA, and then...
Bro, you forgot one of the lines.
Oh, sorry, PA. And then I'm going to factor out the dot product, right? U sub I dot N. And then, this is minus here, right?
Yeah.
So I have U sub I minus U sub R. So where does the 2 come in from? Aha! Here's where it comes in from. Turns out that this is just 2 times U sub I dot N hat.
I mean, it's not too hard to understand why.
Yeah. So basically it's just 2 times the radiation pressure.
Oh, he gave up.
Frick you. You're rude, you're mean, and you're just something else. So that means the force exerted by the radiation pressure is 2 times the radiation pressure times the area of the solar cell cosine squared alpha in the normal direction. Okay, Why? Where does the 2 come from? One
Fucking.
momentum exerted by the incoming photons, another momentum from the reflected photons, hence the 2.
Hey, do you have headphones so Dad doesn't have to hear anything I say?
Okay, so this makes sense?
Yeah.
Great. Oh, napkin.
I think we're gonna cut that one out. I wanna take a
Now,
break.
I'm going to discuss how you can actually calculate the radiation pressure. So this part is really, really cool. So let's really try to understand this, okay?
This part is
Okay.
really cool. Yeah.
So consider the sun. So imagine that this right here is the sun, right? Yes?
Yep.
Now the sun is like a light bulb in the solar system. It emits radiation in all directions uniformly. Does that make sense?
Uh-huh.
So now let's try to understand how much, if you have a solar sail right here, how much radiation pressure is it going to receive? How much radiation will it receive from the sun?
Well, what are the parameters? We have distance from the sun, we have angle, and we have, I guess, velocity.
Yes, so 1 second. So the sun emits radiation isotropically, right? In all directions, right?
Uh-huh.
So let's zoom out. So you can imagine this is almost kind of like a sphere of influence that the sun has.
Or a circle.
Right. Well, in 3D it's a sphere. I'm just representing it as a circle here. So for example, let's say that this is 1 AU, right? That's the distance from the Earth to the sun, about 999 million miles, 95 million miles. And so at 1 AU, the luminosity of the sun is about 3 point... let me just give a...
Is bro about to use candela for the first time in his life?
No, watts.
Okay.
Luminosity is in watts.
Right.
Okay? So the luminosity of the sun at 1 AU is about 3.8 times 10 to the 26 watts. About 4 watts, right?
Mm-hmm.
Let's go out a little further than that. Let's say at...
What does luminosity really represent? Oh, it's mom.
Yeah, how do you know?
631.
Oh.